Okay, can you hear me? Seems so. So, good morning, everybody. So, first I would like to thank the organizers to invite me to this winter school and to talk about magnetic fields. And second, I'd say good morning to everybody of you. So, those of you who don't know me, my name is Beck. I'm from the Max-Planck-Institut for Radioastronomie in Bonn. And my task is to tell you something about magnetic fields in galaxies. That will be mainly done on Thursday. And before I go to the hardcore of the magnetic field observations, I thought I'd give you a few brief introduction lectures, because I don't know about the level of all of you. So I could not hesitate to give a brief summary about galaxies. Then for those of you who know everything about galaxies, they can have a rest or do some emails, so I would not mind. The second part, I will tell you more about radioastronomy. There's a nice radio telescope just in front of this building, but I presume that many of you did not have contact with radioastronomy. Those of you who have, again, can have another rest until the coffee break. And then I will go to measurements of magnetic fields. There will be certainly overlap with what Klaus has told already yesterday. Cannot avoid that. But I think repeating things is not bad. And then I go to the results about magnetic fields in the Milky Way and magnetic fields in external galaxies. So I encourage you to interrupt if something is unclear, if you have questions. I will have brief breaks between my lectures, so you have another possibility to ask questions, so don't hesitate. So if the level at the beginning is too low, then also give me a warning. Okay, we know all that, so you can accelerate, and then I can save time for the other parts of the talks. Okay, so the organizers choose the motto, the elephant in the astrophysical room. So I briefly thought about that. So what does it mean? So obviously it should mean that the elephant is clumsy, it taps around in the room and destroys things and is not a very elegant animal. This is not true. So just last week I had contacts to elephants. I was trekking in the Himalayas, and after that I went to the southern Nepal in a national park, and I understood that elephants are not that clumsy. They are highly intelligent. They are not as clumsy, so they move around very carefully because they are really big. So if you sit on top of them, they are really careful that you don't fall down, and they understand what you're going to do. So I think we can listen to elephants and learn about them, and they're not that bad. So elephants are strong, and elephants are powerful. They have good communication, so they're not as bad as maybe this conference photo tells us. So don't be too negative about elephants. I think comparing magnetic fields with elephants is not that bad, so we can really do that. And then I discovered on a conference in 2004, I had the honor to give the conference summary just to entertain people. I thought maybe Klaus, you were there in 2004 in Brazil. To entertain people, I thought about what could we say about magnetic fields. 2004 was a time where almost nobody really thought that magnetic fields would be important in the universe. So 7 almost blind astronomers study a magnetized elephant. And so the first one does not have a polarimeter and cannot separate the elephant from the background forest. The second astronomer measures the elephant's polarized flux, applies textbook formula, and concludes it must be a mosquito. So don't rely on textbook formula. The third astronomer runs an MHD code, Klaus, of an expanding bubble, and finds sufficient agreement with the elephant. And the other 4 have no idea about magnetism, so they know that the elephant cannot exist. So that was those times. So times have changed, almost 10 years since then, and we have such a winter school here. So we have regular conferences on magnetic fields, at least 1 per year. So now magnetism is really recognized as being important in astrophysics, and that's why you're all here. So you have the idea that it could be important in future, and I can give the prediction, as many of my colleagues will, that magnetism will become really important in the next 10 years or maybe more. It is on the way up to the recognition of astrophysicists, and even theoreticians now realize that they are important, and they are now able to do modeling. And Klaus this afternoon will tell much more about that, and there will be other lecturers telling about that. Okay, so a few basic facts why magnetism was so interesting and important. So most baryonic matter is ionized. That's why magnetic fields are easy to generate. And there are no magnetic monopoles. That's why magnetic fields are hard to destroy. So this is an asymmetry in the universe. So there are electric charges, but no magnetic charges. So we don't have monopoles. And this is why magnetic field can survive over such a long time. If you would have monopoles, then we would all not be here, and I would probably do something different in my research. But they are difficult to observe. So this is the hard part of the story. So hard to observe, but that will be my third lecture, how to do that. So there are still a lot of fundamental questions which will be addressed by many of the lecturers here. How and when were the first magnetic fields generated? I think there will be lectures on Thursday and Friday. What was his name again? Sorry. Yeah. So that will be coming on. Then significant fields, did they exist before galaxies formed? Maybe Fabio will also address on that. I will briefly explain that in my third lecture, right? So how fast were magnetic fields amplified? This is concerning the dynamo. Fausto Cataneo was here last week, and he told you a lot about that. I will briefly give a summary from my personal point of view. How did they affect the evolution of stars, planets, galaxies, and galaxy clusters? So stars and planets have been covered. Galaxies I will cover, and cluster will be covered by Klaus later today. And is intergalactic space magnetic? A highly interesting question. I will briefly touch on that. Maybe also other lecturers will. So again, this is a summary of my lectures. So galaxies, radioastronomy, measurements, the origin, and then Milky Way and external galaxies. I hope I can do the first 4 parts today, and the other 2 parts then on Thursday. Maybe I will not manage to have the lecture 4 done completely today. So it depends a bit on how many questions there are and how fast I can talk. Okay, so let's start with galaxies. Okay, so those of you who know everything about galaxies, now you can have a rest. So I think you need to know a few basic facts before we go to radioastronomy and to magnetic fields about galaxies. So you know that there are spiral galaxies like the Andromeda Nebula and M51. This is a recent Hubble telescope picture. And so just the first question is, where are the spiral arms coming from? This is still an unsolved problem. So in the past it was called to be density waves, and now people are in question about that. So density waves alone cannot do that. There must be other ingredients helping to form spiral arms. So one thing is that their companions may help to excite spiral arms, but there could be other things like magnetic fields that could be important for the stability and the formation of spiral arms, but this is still completely under question. So I would say 90% of the astronomers still believe that it's purely gravitational, but another 10% with increasing fraction now believe that there are other things like magnetic fields, maybe even cosmic rays, who could help to stabilize spiral arms. The barred galaxies are even more puzzling. So why do the bars develop? That must have to do with the large-scale distribution of dark matter. That's what people agree on. Question is how long they can exist, these bars. Are they only a temporary phenomenon? Can they be stabilized over a long time? This is completely unclear. So a bar means that the distribution of matter is non-axisymmetric. And non-axisymmetry means that the orbits of the stars and orbits of the gas are not circular, but they are elliptical. And that means whereas there's a transport of angular momentum. That means angular momentum is transported outwards, and matter can slowly slide inwards into the centers of these galaxies. This is why many barred galaxies have a circumnuclear ring or a circumnuclear bright region. This is the most spectacular picture. This is, by the way, a combination of a photo by ESO and an amateur astronomer. One of the nicest galaxy photos I know. So this inner bright ring is a result of an inflow of matter into the nuclear region. So a blow up into this nuclear region shows a almost complete ring. This is a Hubble telescope picture. And this ring has enormous high rate of star formation, and there is an AGN, Cipher-type AGN in the center. And the question is, how can this AGN be fed? Because these orbits are stable, and there's no reason for the gas to move further inwards. So this is another mystery which has not been solved, and I will come back to that in my last lecture here. So these are phenomena which still need a lot of explanation and work. Galaxies seen in hadron view, they show us something different. They show us expansions, they show us dust lanes. You see this vertical dust lanes. Obviously, they are outflows from these galaxies here. And these outflows are in the gas, mostly in the gas, but not only in the cold gas, but also in the hot gas and also in the cosmic rays. So there's another object, hadron object 4631. And this one here, shown with observed with the Hubble Space Telescope, shows directly this outflowing bubble here. So there's obviously an outflow from the center of the galaxy, and then the center opens up in this bubble-like structure. In the optical, this is H-alpha. This is not that spectacular. In the radio, in infrared, and also in the X-rays, this is much more spectacular. And another class of objects are the ellipticals, another mystery. So they are ellipticals, so not only ellipticals, there are some mixture between ellipticals and spirals. The Sombrero Nebula is something which is odd. So why does it have this disk here? It should not have a disk. Some people believe that this disk formed later. There was an elliptical galaxy, and then there was infall of another galaxy, or several of them, and then the dust lane survived, was built up. The normal elliptical galaxy looks much more boring in the optical. It's just a huge clump of stars, billions of stars here. This is the M87 monster in the center of the Virgo cluster here. Sometimes you see this very strange extensions here, which is known to be a jet, has been discovered in the radio and later also in the optical. So something is going on in the center of that galaxy which leads to a jet and an outflow. And finally, the galaxies which normally don't make it to the textbooks are the irregular and the dwarf galaxies. They are not as nice and bright as the spirals, but they are more frequent. So these are the normal mass of galaxies on sky. And the bigger ones are the Magellanic-type galaxies, like the Large Magellanic Cloud, but there are lots of smaller ones. IC10 is something which is just a big clump of stars with some H2 regions here which are shine up bright in red here, and they're really small ones where cannot be distinguished really from globular clusters. So these are just big agglomerates of several 10,000, 100,000 of stars here. So there is a smooth transition from galaxies to galaxy clusters, and the galaxies are independent, dynamically independent, whereas clusters are bound to another bigger galaxy. But these are form the most of the mass of the stars in the universe. So these are the normal galaxies, but they are not as nice and as bright as the spirals. That's why you don't find so many pictures of them. Okay, so you know the Hubble classification. This is a very crude measure of how galaxies look like, from ellipticals to spirals. Edwin Hubble believed that this is a time sequence, or time sequence from right to left, because these have a large gas fraction and these have low ones. But Edwin Hubble was wrong, so that was not a development here from right to the left, but all the galaxies are formed at the same time, just after the Big Bang. The gas fraction is different because the evolution is different. So the evolution speed of these galaxies are much different. So these develop slowly, and these have developed very rapidly. I'll come back to that in a second. So before I come to the modern theories of galaxy formation, I will just give you a few nice examples of what you can learn if you study galaxies at multi-wavelength. So no astronomer today is just an optical or radio astronomer. So everybody has to study objects in different wavelength. And so this is an example of M51. This is UV in blue and infrared in green and red. And you see that spiral arms are made out of very young stars, which make the UV, and also dust, which is the infrared, whereas the companion is only dusty. There's no star formation going on. That's why the companion is green. So by these combinations, you can learn a lot about the actual star formation rate. So where the dust is, the star formation takes place. But sometimes there's also dust without star formation, and these are also at 3.6 micron, a lot of old stars, which just indicate that star formation has been stopped a long time ago. This famous Bard galaxy, this is infrared and optical with Spitzer. It's similar phenomenon. So the spiral arms are red, which is infrared, and blue, optical, and this companion again is blue. So these are only old stars here, and this bright inner part is really bright. It's overexposed in both, so it makes a lot of stars and also has a lot of dust here. So M104, the Sombrero Nebula, and you can see really the differences. So in optical, you see the main bulk of the stars. In infrared, you see only the ring, which is a dust ring, and in infrared, you see a large distribution of X-rays, which is partly diffuse and partly stars here. So this is nothing is seen of this dust here. So the dust, the cold material, and the very hot material and X-rays, they have very little relation to each other. And similar for Hadron galaxies. So this Hadron galaxy has a bright, this is H alpha disk here, a star formation like a boiling, looks almost like a volcano, like a lava flow, but the X-rays, they are much lighter, much hotter, so they can expand and they form these big X-ray halos, which are seen very frequently in many of the Hadron galaxies. And then our neighbor, M3031, there's a recent very nice picture from the Spitzer telescope, just with different dust temperatures here. So the inner dust temperature, the inner part has a high dust temperature, the outer part is a low one. So red is a low dust temperature, and blue and white is a high dust temperature. So the dust in the inner part of M31 is heated by a large number of stars, which are existing in the inner part of M31, whereas in the outer parts, the dust has much lower temperature because the star formation is much lower, and star formation has just started in this outer part of the galaxy. So M31 is a very strange example where the star formation was very high in the inner part some time ago, and now the star formation is mainly occurring in the outer parts of that galaxy. And the UV, that confirms the similar pictures. So you have a UV mainly in the outer parts, in the outer spiral arms where the star formation is actually going on, whereas in the inner part there is nothing going on. This is just an optical picture in the background where you see just a bulk of very old stars. And in X-rays, you don't see the spiral arms again. Not at all, because the star formation rate is much too low to produce a lot of X-ray emission. What you see here is mainly X-ray binaries, and a lot of X-ray binaries in the inner part and a few ones in the outer spiral arms, so you can hardly say that this is a spiral galaxy here in the X-rays anymore. And finally, so there's a cold dust, but there's also cold gas, cold hydrogen, which is measured in the H1 line in the radio. And the H1 shows that it's not only this ring here, which is actually star forming. There's much more gas in the outer parts of the galaxy. And this is typical for all galaxies. If you look in the H1, the material, the building material for the stars, the hydrogen, and the hydrogen extends much, much further out. And the question is this infalling gas, or is this just the outer parts which have been left over from the formation of the galaxies? Also, that is not a clear, not an answered question anymore. Come back to that in my next lecture. And if you then wait a bit, then stars start to form, then the material starts to clump and starts to become molecular. So this is molecular gas, mainly hydrogen, but molecular hydrogen is hard to observe. That's why you go to some other lines which trace molecular gas. The best is CO line. So this is a CO picture of M31. So all the outer gas is not seen because it has not clumped yet, so the clouds have not been formed, smaller clumps here, and all these different clumps, they will form stars within the next few 100,000 years here, and so you can make a computer simulation out of that image, how M31 would look like in a few million years here. Okay, so basic properties of galaxies, typical sizes are a large range of orders of magnitude from 10,000 to 10 billion light years. Number of stars can also vary a lot. The mass can be between 10 to the 8 and 10 to the 12 solar masses from dwarf to elliptical galaxies. The gas mass has a somewhat smaller range, so 1 million or 10 million solar masses, maybe a bit more. The dust mass is typically a factor of 10 lower than the gas mass. Rotation velocities are of that range between 100 and 300. Rotation period between 10 to the 8 and 10 to the 9 years. And as I mentioned before, galaxies practically have all the same age. They all are 13 billion years old. There's no galaxy formation since then possible anymore, with very few exceptions. So there are some tidal tails where there are maybe small galaxies formed, but this is extremely rare. So one can say that galaxies practically have the same age, in contrast to what Edwin Hubble thought 100 years ago. So how does our own Milky Way fit into this general picture of galaxies? So you can have a wide-angle picture of the Milky Way, and you see immediately that our Milky Way looks very similar to an Hadron galaxy. So that's why people believe that this is a spiral galaxy. This is 891, which is very similar. So you can flip back and forth, and so this is really looking extremely similar. You see these dust lanes and everything like in Hadron galaxies, and that's why we believe the Milky Way looks like something like that. Maybe not as nice. We know that the spiral arms are not very pronounced. Maybe it's something like this one, and we are somewhat out there at a distance of 7.8, roughly 8 kiloparsecs, which is roughly 25,000 light years here. So we believe that there's a black hole in the Milky Way center, which has been discovered by the orbit of many stars, which have been traced in the infrared here. So the mass of the black hole in the Milky Way center is at least 1 million solar masses, and the data are getting better and better. So that let us suspect that most galaxies have a black hole in the center, but they're very hard to observe. Also, our own black hole in the Milky Way center is not active, so we cannot see it in the radio. That's why it's hard to observe. It's also very hard to see even in the infrared, so there is something seen there, but it's not clear whether it's really the center itself or just some of the stars around the center. And the other fact is that not only a black hole in the center, there's also dark matter in the outer parts, because the rotation curve is flat, and this flatness of rotation curves you're all familiar with. This is a strong indication for dark matter. So I will come back in my last lecture to the question, could the flat curves be magnetic? Could that be something completely different? But the answer already, I can say now, is no, we cannot explain this by magnetic fields. It's a nice idea. Some people believe that this may work, but in fact it does not work. So the visible matter only gives a rotation curve about that size. So the sun's velocity should be around 160 kilometers per second. In fact, the sun's velocity around the galactic center is 220, and the curve is flat, so there must be a lot of dark matter. Sorry, magnetic fields don't help here. Would be nice, but it's not the case. So if you just scan the Milky Way in different traces, you see that there's also a lot of hot gas, ionized gas, traced in the optical H-alpha line here. So it's quite spotty here. You can see some of the spiral arm structure on which we are sitting, but even the inner part is very clumpy, and this is clumpy. And this is not in the galactic center, but these are nearby clouds of star formation. And the distance of these clouds is only a few kiloparsecs. In H1, you can look through. You can have an integration of the whole line of sight, and there you see the Milky Way plane much better. You can see some extensions here, but otherwise it looks really like the Hadron galaxies. There seems to be some flaring. If you go to the outer parts of the galaxy, it seems to expand, and this is what we believe is due to the smaller gravitational potential. So all the layer of the H1 is expanding because the pressure is lower, and so it can become more extended. In CO, it's different. CO is much more concentrated to the plane here. It's much more narrow because CO is heavier. It has a larger mass density, and that's why it's concentrated, whereas also in the outer parts there is more fuzzy stuff, but this is the nearby stuff here, whereas this is more in more distant parts of our own galaxy. And in X-rays, again, things look completely different. In X-rays, we don't see stars, we don't see the gas. We see local features like this big one, which is the North Polar Spur, which is probably the relic of an of supernova remnant a few 100,000 years ago. The plane itself is absorbed, so this is typical that the gas in the plane absorbs X-ray, and otherwise there's a huge halo, this red color, a huge halo of X-ray of hot gas around the Milky Way. Okay, so the Milky Way has, as I said, several components. It has cold and hot components, molecular clouds. We have temperatures of only several 10 degrees. Then the cold neutral medium seen in H1 up to 100 degrees. There's a warm neutral medium up to 10,000, partly seen in H1, partly seen in H-alpha. The warm ionized medium is seen in H-alpha, the H2 regions, and then the hot coronal gas, several million years, which is seen mostly in X-rays. So there's a lot of discussion about the filling factor. So the molecular clouds have probably less than 1%, the cold medium a few percent. Most of the volume filling factor is the hot gas, which has about fills about half of the volume of the interstellar medium. If you compare the pressures, they are quite similar. Pressures are not in here, but you can easily compute it from the temperature and the density. So you just multiply these two, then you find that the pressures are quite similar between all these components. So there's some sort of equilibrium between the different components of the interstellar medium. Yeah. The masses are not from the. So you mean the total masses? Yeah, I think the neutral gas has as I said, has several per galaxy, several 10 to the 6 solar masses. The molecular gas several 10 to the 5, and the ionized gas is completely negligible. I don't know about the mass, but it's certainly 10 to the 4 or even less solar masses. Yeah. The coronal, I think this is probably very low. Close to you happen to know? Probably 10 to the 4, maybe less than that. So from the mass, it is completely negligible. H2 regions also, it's only a small fraction, so that doesn't play a role. So most of the mass is in the cold and the warm neutral medium. The warm one is unimportant, and molecular and hot is also not important. Of course, everything is much less mass than the stars, so the stars always dominate in the total mass. Okay, I will not mention clusters, just show you a few nice pictures, because Klaus has talked about that yesterday. So just to remind you, there is a big cluster nearby in the constellation of Virgo. That's why it's called Virgo cluster. So our Milky Way is this small spot in the direction of Virgo at 50 million years ago. There's a big cluster here, which is extremely exciting. A lot of studies can be done. In the optical, there are hundreds of galaxies here you can study. That's why it's very hard to get observation time around that sidereal time, because it's so exciting to observe there. In H1, there's a lot of gas has been. A lot of galaxies have been studied, and as you can see, the color indicates the velocity. Velocities are not very uniform, so there's a lot of proper motion within the cluster of galaxies. Yeah, but this is something Klaus has touched, and he will come back to that this afternoon. In X-rays, there's a lot of X-ray emission, and this is another indication for dark matter, because the number of galaxies, the mass of the galaxies, is not sufficient to hold together this hot gas. So if this hot gas is stable, it has to be stabilized by dark matter, and this is another strong indication that dark matter is really needed. Otherwise, the hot gas the pressure is so high, it would just evaporate within a short time. Okay, so fundamental questions about galaxies. So what do we have to learn, or what do you have to learn if you decide to work on galaxies in your research? What is the full extent of galaxies? What we see is the tip of the iceberg. So how large are galaxies really? So we can see galaxies only where the stars are existing, or where the gas is illuminated. Very cold gas is very hard to see, because if its temperature is low, you cannot see that. How are spiral arms formed? This is an open question. What is dark matter? Of course, very interesting question. And how are magnetic field forms? This is my lectures 4 to 6. When and how were galaxies formed? I will briefly touch on that now. And what is dark energy? This is another problem which is very hard to solve, but galaxies may help on that. So when and how were galaxies formed? So there are a few basic facts which we know. So we know that galaxies have distributions like big rings. So obviously the distribution of galaxies in the universe is not uniform. And this has been confirmed by simulations. So this is a simulation Klaus has done of the structure formation in the early universe using just dark matter without magnetic fields. Maybe I can show something with magnetic fields this afternoon. So you see that these structures here, and so all these filamentary structures, so this looks like a Virgo cluster and Hydra cluster, and our Milky Way is somewhere in between here, where the density of gases is relatively low. So there's some indication that with structure formation in the early universe, you can really understand why galaxies are that differently distributed. If you now go down to the individual formation of the galaxy, things get much more complicated. So the classical picture was that a big clump of gas, a proto-galaxy, that is rotating very slowly, that may become elliptical galaxy, because all the material can be transformed into stars. Whereas the spiral galaxy is rotating fast, and because of angular momentum, only the disk can form stars, only the halo, the outer parts can form stars, whereas the gas, the remaining gas, just falls into the disk and forms stable orbits, and in these stable orbits cannot form stars anymore. So this is a classical picture. So he just claiming that the differences between galaxies just purely due to angular momentum. But this is probably not correct, and the modern picture says that interactions play a major role for galaxy evolution. And probably all galaxies suffered a major interaction and could completely change their appearance. So something like a close encounter here, the mice galaxy, or even more dramatic, the antenna. These are types where two spiral galaxies merge. Then they probably become an elliptical galaxy. So they can change their appearance completely by merging. And these merging and interactions obviously are very, very frequent in the universe. So probably galaxies are not isolated objects. They are just changing their appearance due to interactions with other galaxies. And then at the end of this lecture, just a brief remarks on radio galaxies, so things which I'll come back in my next lecture. So radio galaxies are objects which are dominated by the AGN, by the core. So this is the largest and the brightest radio galaxy in this constellation of Centaurus. And this is just not a very suspicious elliptical galaxy. In the optical, this is a square here, but in radio, there are two huge lobes. So these are AGNs which are obviously fed by material. They become very bright, and then they form eruptions here, like Centaurus A. This is in X-rays here. You see that things go out here. They are forming big explosions here. And even more dramatic in Cygnus A, in the brightest galaxy in Cygnus. This is a very small and unsuspicious optical galaxy, but in the radio, this is one of the brightest objects on sky. So the optical is just this small spot here. There are huge lobes here, and here you can see the jets here. So there's obviously material transported outwards from the AGN. And this is probably something to do with the black hole in the center of the galaxy. So these jets are supersonic streams, and we are sure that these jets must be magnetic, otherwise they cannot be stabilized. And if you combine radio telescopes all over the world and go really deep into these jets here, then you can resolve these small parts of the jets more and more with higher and higher resolution, and you can trace the jet very well to the inner part of that object here. And so this is just the light year of resolution here. And these are probably what we call magnetic whirlpools. So you have black holes, and there's material falling in, and then some part of the energy can be translated outwards on the jets and form these big lobes and the jets we can see in the radio. So another big, this was the last point of this lecture, point concerning galaxies is that we have learned from galaxies that the universe is accelerating, expansion is accelerating. And this is not due to dark matter, so we need something else. We need the dark energy, and the dark energy is a complete mystery. So we have no idea what dark energy is. So if we have no idea, we have to measure it. And how to measure that? We just have to trace back the expansion. We have to measure the expansion of the universe as good as we can. And as good as we can means we have to trace as many galaxies to the to the time where the galaxies were formed, which was about 1 billion years ago, and measure as many galaxies as possible with the help of optical or H1 emission lines. So this is a big task for the future, and there are many projects trying to do that. So if we measure the expansion of the universe to a very high precision, then we may understand better what the result of dark energy is. We still don't understand it, but maybe we can learn a bit more about that. And this is something I will not do anymore in my scientific career, but maybe you will do, and hopefully successfully understand what dark energy really is, and galaxies help with that. Okay, so that was my first part. So are there immediate questions to that? So that was basic level. Now we are slightly increasing the levels. So I think everything was clear. Yes, okay, of course. I did not say they do not. I said that's not sufficient. That density waves alone, this is not sufficient to do that. Let me just try to get that out. The point is that the density waves can do it, but that survives only for a limited time, and especially the stabilization of the spiral arms is a problem. So you need something to stabilize the spiral. For instance, if you don't have a bar, if you don't have a companion galaxy, then it's very hard to form spiral arms. So you need some non-axisymmetric disturbance to make spiral arms. Then it's easy. If your companion, like in M51, okay, then no problem. If you have a big bar, it's no problem. But if you have a normal galaxy like M31, so what's then? Yeah, that's a possibility. Yeah, but it's not if your bombardment of things, then it will not produce this strong non-axisymmetry. If you have a major merge of something which is really falling in, M31, this is discussed. There was one of the companion galaxies was passing by recently. It has an orbit around M31 and could continuously excite the spiral structure. This is one model. But these are things which okay, they may work, but I think with magnetic fields things are much easier. So they can build up extra pressure and just stabilize the spiral arms. If they're once excited, they can just help that they survive for a longer time. But this is completely open. This is just speculation, I would say. So it's not proven that density waves alone cannot do that, and it's also not proven that magnetic fields can really help. It's just ideas which are in some people's mind. Okay, so next part, ready for the next part. Okay, radioastronomy. So radio astronomers, please have a sleep, and now I give you a very brief summary of why radio astronomy is very fascinating, why I decided after my diploma to do something else and to move to this very nice telescope here. This was freshly opened, and I thought this is a good idea maybe to do something different, because I was really bored with stellar spectra. I didn't like that as a student. Okay, so what is radio astronomy? Radio astronomy is doing astronomy in a very big window. So this is a window where the electromagnetic radiation can go to the surface. Compared with the optical window, it's really big. You can observe from several millimeters up to several tens of meters. And this is normally called the FM range, the decimeter range, the centimeter waves. In infrared, it's difficult. You need high mountains, or you need satellites here. And UV and X-rays is even more difficult. There's a limitation of the radio window to long wavelength. This is the ionosphere. The ionosphere works like a mirror. So there's no radio emission coming to the surface of the Earth beyond 10 meters, 30 meters roughly. It depends a bit on where on Earth you are. So if you really want to go to this very long range, so the long wave and medium waves, which has been existing in the old radio receivers, then you have to go up to space or on the moon. So from the Earth, you can your end of the radio. The radio is determined by the ionosphere at about 10 to 30 meters. And the small wavelength, it depends a bit where you are. It depends on the atmospheric conditions. If you are high on a mountain, you can still observe at a few millimeters on the ground. Then you're at a few centimeters. It's the end of the story. So this is one problem, the ionosphere and the atmosphere. The other problem is the commercial use of radio waves. So this is not the latest one, but allocation of radio frequency bands. So each frequency band has an allocation. So you cannot put your radio telescope where you like. Okay, you can do, but you would not see anything from the universe because there's a lot of commercial usage. So also only the purple parts here are assigned to radio astronomy. So small parts we are allowed to use. So if you use, so this is 6 centimeter, for instance, then you're mostly fine. But if you decide to go to higher or lower frequencies, then you have to compete with other usage of radio frequencies, and that means you have to face with so-called man-made interference or with artificial radio signals, RFI. And this is a big problem for modern radio telescopes. So in the past, we were happy with our small gaps. We were just assigned, but now we want to use much more frequency band, and then you have to fight. That's one possibility. Yeah. If you want to avoid the FM band, go to Western Australia. So this is what is done. But here, of course, you cannot use the FM band. If you go to remote places, it helps, but this does not really help because the satellites for instance, are everywhere. They are seen everywhere. So it's you have to overcome. So the modern radio astronomy has to fight with RFI, and that means the tools and to remove artificial signals, which is the most important part of modern radio astronomy. We would like to have larger bands, but it's too late. All that has been sold, and this is really money. This is billions of dollars here, which is that worth of the radio bands here. Okay, so in 1887 things were much, much better because nobody knew about radio waves, and Heinrich Hertz in Germany discovered the radio waves in a lab in Karlsruhe, so none of his colleagues really recognized how important that is, and he had a long time to convince people that this is real, so you can really transmit energy from one part of his lecture room to the other part, and the lecture room was really big, much bigger than this one here, so you could show that it works. But still, that there could be radio waves from the universe. This was only recognized 50 years later, so by Carl Guth-Jansky, by the radio engineer who built this radio telescope, not to observe cosmic radio waves, but he was engineer of Bell Telephone company, and to improve the transmission of telephones via radio waves. And then as a byproduct, he made a map of the sky, so where he found strange radio signals, and the highest signal came from the constellation of Sagittarius, but he has no idea what Sagittarius means. Sagittarius, of course, we know it's the center of our Milky Way, but in those days it was not known. People believed that Cygnus was the center of the Milky Way. So he had no idea what that should be. And an amateur astronomer, Roter Reber, he made a similar map, confirmed that the largest radio emission is coming from Sagittarius. At that time, there was an idea that maybe this was the real center of the Milky Way, and he confirmed that at a different frequency. He built a modern-looking parabolic dish telescope, and he was much more recognized than the engineer Jansky, and this was a breakthrough of modern radio astronomy. Then briefly after that, the Second World War came, and there was a lot of production of radio telescopes, but for war reasons, for just defense, and many of these relics, the German relics, were left over at different parts of Europe, and they were used as the modern first radio telescope to do experiments. So the first really big telescope, the parabolic dish, was built in England, in Jodrell Bank, at the same time also in Green Bank in the United States. This was a very light construction which should last only for a few years. It lasted longer, but at some stage it was the end of the story. The construction crashed, And that was the reason why US then built a new telescope. We'll come back to that later. So a bit later than the Effelsberg telescope was established. It was more than 20 years the largest steerable dish in the world. So this is our Institute's telescope here. It operates between a few millimeters and a few decimeters here. And so we have different focal planes. We have a primary focal plane and a secondary one. And this backpack-looking thing here at the secondary focus cabin hosts a big receiver for 11 centimeter here. All these receivers are built in a similar way. So we have left and right-hand circular polarization recording from the horn, and these are correlated and give us also the Stokes parameters in linear polarization. I will come back to that in a second. But for purpose I will show in a second, we also use secondary focus receivers with multi-horns. This is a multi-horn receiver. This is one here, and this is one which is sitting out there here for 6 centimeter wavelength. So multi-horn means that there are several points on the sky observed at the same time, and that has big advantages. So we have single focus receivers in the secondary and primary focus. We have multi-horn receivers in the secondary focus. These detect circularly polarized emission, and the circular is then transformed in a digital correlator to form linear polarization in Stokes parameters U and Q. So what are the Stokes parameters? Stokes parameters describe the vibration plane of the polarization. I've turned this by 90 degrees because this is the astronomical convention. So a Q signal, plus Q signal is in the north-south direction, or minus Q in the east-west direction. Plus U is 45 degrees tilted, and these are the circular polarized. So plus V is counterclockwise, and minus V is clockwise, circularly polarized emission. And you can see already that polarization planes are now vectors here. People call them vectors, but in fact they are not. They are vibration planes, so you cannot distinguish whether the emission is going north or south. It's just a north-south vibration plane here. So that's how raw maps of the Effelsberg telescope look like. So if you want to do an observation of the Effelsberg telescope, it's highly encouraged. It's very simple. So you're scanning a region on sky over a large region. So this is at 3 centimeters, 8 gigahertz. You have only one point on sky, so you cannot do a map of the whole area. You have to scan it line by line here. So you scan it either in this direction or perpendicular. There's an advantage for that. And this is Stokes I, this is Stokes U and Q here. So just to show you that these stripes which you see here, these are weather effects which you have to overcome, and they can even seen in polarization. So how to overcome weather? You do it in 2 different directions. Then you do a fast Fourier transform, and then you can overcome these stripy things here. So that works quite well. So this is before, this is after. So you see the image is almost clean, and the scanning effects have disappeared, and in polarization it also works fine. So these are standard methods which allow us to map relatively large areas on sky without having major problems with the weather. Okay, if it's raining like at the moment, we cannot observe. This is too bad. So you need at least a relatively good sky. So a few clouds can be accepted, but not more than that. Another way to suppress effects of weather is to observe with 2 horns. So this is with dual horn observation. So this is a source seen with 1 horn and seen with the other horn. And by a combination of these 2 images, you can also overcome the weather. So this is a reason why we have many dual horn receivers. We would like to have a receiver with maybe 100 horns or 200 horns, like a CCD camera. But this is not possible at the moment because to build a receiver, an amplifier for a single horn is very expensive, and you can do maybe 5 horns, maybe 10 horns, but not more than that. This just doesn't work. You have to go to different techniques. And as I said, so RFI, if you are at 3 centimeter wavelength, then the assigned range for radio astronomy is extremely small. Our band is much larger, so you cannot complain if there's somebody just spoiling your signal. So you just have to overcome that. And these are still good. This is a good observation. There can be many of these RFIs during mapping an area on sky. So this is becoming more and more a problem. And this, as I said, the tools to remove these things are getting very important. So, as I mentioned before, the Green Bank telescope has crashed, not completely unexpectedly, because it was a lightweight construction, but in the United States this was seen like a national catastrophe, so they really thought we have to build a bigger one, and of course a bigger one than the Effelsberg telescope, just to get back the world record, and that's why the GBT is 102 meters effective area. And this is a different construction. It's not symmetric. It has a one, so there's the focal plane, the primary focal plane is on these two-armed things, so that the aperture is less blocked than the Effelsberg telescope. So it's very good for spectroscopy. It's not good for polarization. Arecibo is the largest dish on Earth. This is not movable. It's 305 meters, has recently been refurbished, so now it can observe a relatively large area around the zenith. You can move the focus a bit, but of course you cannot observe the whole sky with that telescope. And we should not forget that the biggest radio telescope is Ratan 600 in Russia. We don't hear much about that because the scientific results of that telescope are extremely poor. The reasons are not known. Probably the construction was just a failure, and to build a big ring here and then have a focal plane like this cylinder here, that obviously did not work. But it's really nothing really I know about important discoveries made with this radio telescope. But still, it's the biggest one. It's 576 meters here. Going to higher frequency, smaller wavelength, as I said, then you reach the problems of atmosphere. Then the atmosphere is really disturbing you, so you have to go to higher mountains. So on Pico Veleta in southern Spain, there's a IRAM 30-meter telescope for the millimeter range here. And then for the sub-millimeter range, the most capable telescope at the moment is Apex in Atacama in Chile, can go down to 0.2 millimeters. This is the last window you can really observe from the surface of the Earth. If you want to go to higher frequencies, you have to go to planes or to satellites here. And the Apex telescope is a prototype of the ALMA interferometer, which is now operating. It's by the ESO observatory. So besides of the single dish telescopes, we have also the possibility to build interferometers or synthesis telescopes. So a telescope size determines the resolution of a telescope, and the radio astronomy resolution is not very good. So because the wavelength is long, so that's why more than 100 meters are not possible. In the United States, there was an idea to build a 150-meter telescope, but then the engineers said, okay, that will not work. Just the gravity on Earth is just too large. So you have to do this on the moon, which is too expensive. And much cheaper is to build an interferometer. So this is one of the first ones in the Netherlands, in Westerbork. And this is a VLA, which is the most famous one. This Y-shaped telescope here in Socorro. It can be modified to different configurations. This is a compact one, and then there's a big car transporting the telescopes one by one out into the desert. It can be expanded up to more than 25 kilometers baselines here. So angular resolution, as I just mentioned, is determined by the wavelength and the diameter. Wavelength is relatively long. That's why with the Effelsberg telescope, in spite of the 100 meters, you have a resolution about similar to the naked eye, about 1 arcminute. So if you really want to have images which are better than what you could see with the naked eye in the optical, then you need interferometers. With the VLA, then you go to the arcsecond or sub-arcsecond resolutions. This is why interferometers are so popular. But they have also disadvantages, and I'll come to that in a second. So this is a typical configuration of the VLA. So all these points are telescopes. They have their fixed points on the rails here. And if you do a snapshot observation of this telescope, this is what the telescope would look like. The telescope interferometer observes in the so-called UV plane, which is something like a virtual plane on the ground, which a telescope would see. So it's not a filled dish, it's just a point-like structure. And that's why an image made with such a telescope has this point spread function. That's what a point source would look like. Okay, so for very bright sources that may be sufficient. But if you go to weaker sources, you see all these artifacts here, they will kill you completely. You cannot detect any diffuse emission. So you have to observe longer, for 12 hours, for instance. Then here your V-plane gets much better because all of these points start to rotate, seen from the source, rotate on the ground, and that corresponds to a telescope which is almost completely filtered. Then you get a really good point-like image of the source. So you have to observe for a long time with the VLA. And that also depends on the declination. So if you have high declination, everything is perfect. But if you go to lower declinations, you can observe up to -30 with the VLA. Then your UV coverage does get somewhat distorted. Then things get worse. But in principle, you can still get a very good image of a source and also get the diffuse emission well observed. There's one big disadvantage of interferometers. They have a strange shadow around that. So this is a diffuse emission of a galaxy here. And you see these white areas, these are negative areas in the image. And these negative areas are the result that there's some part the telescopes cannot cover. This is a distribution of baselines here. This is a blow-up of that, and there's a gap here. And this gap here is because you cannot move the telescopes next to each other. The shortest baseline possible is the distance between the two nearest telescopes. And this part is missing here. And this part corresponds to these shadows here. So some of the large-scale emission is missing in such images. But we have single-dish telescopes. So Effelsberg can cover that. Effelsberg is a 100-meter telescope, so it covers everything from here to 100-meter baseline. And 100-meter in kilo lambda in 1,000 wavelength is around 3,000 wavelength here. So you can combine VLA with a single dish, and this is what is done here. This is how the VLA looks at that, and this is how the Effelsberg telescope looks at that. And if you combine, you can recover the full emission. So that can be done for VLA. It can be done also from the millimeter range for ALMA, together with the IRAM telescope. So this is now a classical way of combining images. Okay, so this combination is crucial to fill the missing spacings. Okay, so enough about the basics. Now I would just give a few results on what radioastronomy has done so far. So just a very brief trace through the history of radioastronomy. So the history of radioastronomy is full of Nobel Prizes. So radioastronomers were quite successful. And one by-chance discovery was the cosmic microwave background by Penzias and Wilson. They had no idea what they were observing, but they had a few colleagues who could tell them what was going on, and interpretation was most probably correct. So the microwave background was discovered, and the Kobe did that in much more detail and got a second Nobel Prize for the CMB. And then the WMAP came, did it even more detail, and at the moment this is the main discovery of this power spectrum with the oscillations, which gave a very strong indication that the idea of cosmic evolution is basically correct. And what we see here is the first indications of structure formation in the universe. And at the moment, Planck is running. Planck started in 2010, and we have a very nice map of the radio sky, and after subtraction, everything which is in the foreground. Then just last year, early this year, the new map of the CMB fluctuations was published, and that was even more refining the ideas about the evolution of the universe and the structure formation in the very early universe. So the second important discovery is the discovery of the line of neutral hydrogen H1 at 21.1 centimeters. That was in the early 60s, as far as I remember. So this is the change of the spin between the electron and the proton of the hydrogen from antiparallel to parallel, so absorption or emission. And this is the strongest line in the universe at all. So if there's interstellar communication between civilizations, this is the wavelength to go. So this is universal wavelength, and I've already shown you what it can be done. you can observe galaxies in H1, so you see where the potential star formation is still existing, but you can do more. You can measure the radial velocities, because you know where the line should be, and you can measure the differences, and you can see a galaxy rotating. So this is an online image of the rotation of this galaxy here. So it's here, it's coming towards us, here it's going, no, this is going away from us. This redshift is always the other way around, and this is coming towards us, the blue parts here. And that can be extended also to molecular lines here. So molecular lines are those who are existing in dust clouds here, infrared. You see a few stars highly reddened here. But in radio, you can see emissions like CO or formaldehyde at different wavelength, where you can really see emission from these dust lanes, from these dust clouds here. And this is what you already shown you before. This is CO and M31, all these different clumps. And the same in velocity field. You see a much more detailed velocity field in M31. You see the general trend of the rotation, but if you look in detail, you can see a lot of different things, like you see clouds which have a wrong color here. This is a cloud which is orange, here's a cloud which is green, and that is not according to the local rotation velocity. So you see a lot of proper motions of these clouds if you study these clumps in CO. So you can see expansions, you can see all sorts of missions here. Okay. So these radio lines can be traced even at extremely large distances. So this is water vapor at 6.1 gigahertz, and there was a few years ago a discovery in a galaxy core, which is amplified by gravitational lensing at a redshift of, I don't remember, so this is 11 billion light years, so a redshift of 2 point something, and this was a very strong detection here. And by help of gravitational lensing, you can detect these molecular lines even in very early universe AGNs. And there was a surprise that even at those times in the universe, we can find a lot of molecules. Also, CO has been detected in many of these distant galaxies. Okay, and the main field I'm working on is synchrotron emission. So this is another way to measure radio emission. Synchrotron emission has nothing to do with molecular lines and has nothing to do with CMB. It's just electrons who spiral around magnetic field lines. So if the electrons are fast enough and the magnetic field is strong enough, you can detect radio emission. And this is why this is a Milky Way in optical light. The sky, which has been observed by Jansky already almost 100 years ago, in fact is a map of synchrotron light, and in fact it's a map of magnetic fields illuminated by cosmic ray electrons. So all what you see here are practically interstellar magnetic fields. So you don't see any stars here on such a radio map. You can see only a very few known features. So are the Magellanic Clouds here, the large and the small one. And Centaurus A is a radio galaxy here, which can be seen here. This is a Cygnus complex here, full of supernova remnants and magnetic fields. And you can see this north polar spur I've mentioned already in X-rays, which is probably the remnant of a nearby supernova. So this radio sky is completely different from the optical sky. So what you see here is mainly magnetic fields here and nothing else. And if you zoom into the center of the Milky Way, you can trace the center. It's almost the center itself. So there's this nice spiral structure in the Milky Way center, which is not a spiral structure like in external galaxies, but it has to do with infall and outflows around the nucleus. We don't fully understand what's going on here. And in the Milky Way center and many other places, we find these remnants of supernova remnants, of supernova explosions. This is a supernova of 1667 called Cassiopeia A, which has still an expanding shell here. We can observe the expansion by observing the radio emission every few years here. So these supernova remnants are very bright in the radio because they have magnetic fields and they have ejected cosmic rays. So the supernova produces cosmic rays, the supernova shock front produces cosmic rays, and this is why these objects are so very bright in the radio. So very rarely we see an actual supernova exploding on skies. So this is the one in the Magellanic Cloud, which was detected first in the optical here, very bright, and then also followed up in the radio. And if you wait long enough, you can see the expansion of a supernova over the years here, from a small shell to a larger and larger expansion. So that can be watched online with help of radio astronomy, sometimes also with optical, but in radio this is much more easy to do. So sometimes these supernova explosions, they have a relic, they have a neutron star in the core, and that was another Nobel Prize for radio astronomy when the PhD student Jocelyn Bell discovered with a Cambridge 80 megahertz telescope very strange signals at certain positions on sky. She had no idea what that could be, but her supervisor also did not have any idea, so they was discussing what could be. Could it be signals from extraterrestrial civilizations? But they just keeping that closed because they didn't want the press to make a big fuss out of that until they had a different alternative view. And so they discussed it, and then the idea came up that could be a neutron star, just a relic of a supernova explosion. So that prevented big rumors in the press. So this is the Discovery pulsar. Of course, the Discovery was not as nice as that. This is a recent observation of that pulsar here. It has a spin period of 1.3 seconds, and as you all know, this is due to the emission along the magnetic axis, which is tilted against the rotation axis, whereas the neutron star has a very strong magnetic field. But the emission process, just to tell you, is not understood at all. So we still don't know what the radio emission of a pulsar produces. There are different theories, so this is much too far beyond the topic of this lecture here. Another Nobel Prize here for pulsars was this double pulsar here, the Hulse-Taylor pulsar, which is decelerating and losing energy, and the energy loss of this system is exactly as predicted for the emission of gravitational waves. So that was the indirect detection of gravitational waves, which gave another Nobel Prize. Okay, now slowly moving to the work I've been doing and just introducing you into the world of synchrotron emission and how to study magnetic fields. This is, again, a map of M31 of the Andromeda Nebula, now observed with the Effelsberg telescope at 6 centimeters. So again, you see this nice ring we have already seen several times. So this nice ring, and this now is a ring of magnetic fields. And this ring corresponds to where the star formation is going on. Where the star formation is going on, we have supernova explosions, supernova remnants. Supernova remnants produce cosmic rays, and the cosmic rays can illuminate magnetic field. It does not tell us that the magnetic field is only existing in this ring. Magnetic field can be much more extended, but we just see it there where the cosmic rays are accelerated. The cosmic rays cannot propagate far away from their origins, maybe a kiloparsec, maybe 2, but not further away. So that's why we don't see any radio emission from these inner parts here of M31. There are millions or billions of stars in the inner part here, but these stars don't produce cosmic rays because these are old stars. That's why we have these holes here in the inner part. There's the center itself, which is a different story here, but otherwise we see emission from this ring structure. So the ring is a ring of star formation. So the magnetic field in the ring of star formation is illuminated by the cosmic rays. And the lines here are the so-called vectors, are not real vectors, but they are pseudo-vectors here, which indicate the orientation of the polarization plane. So in radio astronomy, it's very simple to measure polarization, because degrees of polarization are up to 40% in that areas here, 40. So not like in optical. My next lecture I will explain this. Very difficult to do this in the optical. In the radio it's much, much easier. So 40% polarization, and the polarization plane rotated by 90 degrees gives you the orientation of the magnetic field. And that indicates that the magnetic field indeed is along this ring here. So that was a big discovery we made several decades ago. So the typical spectrum of a galaxy, this is a log-log plot, this is frequency, this is brightness, gives a more or less linear decrease here, which is a so-called power law, almost with a slope of 1. So this is the synchrotron part here, and then at the high frequencies it rises up again. This is not synchrotron anymore, this is the dust emission from the dust within these galaxies. And then there's a small free part, this is the thermal emission, which is weak, but it contributes to some flattening in the spectrum. I'll come back to that in my next lecture. And at the end of this talk here, I would like to give you an outlook over the new telescopes we are building at the moment, or we hope to build in near future. So what we need is higher sensitivity, higher resolution. And the standard argument is the universe expands, so we need larger telescopes. I don't know whether the committees will accept that argument. So one thing you could do, you could increase your baselines. So increasing baselines means you can combine telescopes at different parts of the world between, say, Hawaii and Europe. That is the maximum baseline you can do. Okay, Europe, Australia is a bit more difficult because you have to do simultaneous observations. But this is not yet sufficient. So you reach something like a bit more than a milliarc second resolution. This is not good enough to go really into the deep centers of galactic nuclei. So what else could you do? You could decrease your wavelength. You could go to millimeter or submillimeter. And this is what is done at the moment. So the millimeter and submillimeter telescopes existing on Earth, they will be combined. So this is the CSO on Hawaii. This Kitt Peak. This is the old Heinrich Hertz telescope. The new one, also Apex, the Pico Veleta in Spain, Plateau de Buer in France, and then the Apex telescope and ALMA in Chile. So with these telescopes, if you really go to 345 gigahertz, which is about a millimeter, then you can reach between 16 and 20 milliarc seconds. And this is something people are very excited about because there are simulations how to detect the black hole in the galactic center. So the black hole in the galactic center should produce some sort of shadow. The black hole, of course, is much, much smaller, but the shadow, which is the distorted space around the black hole, which should distort the emission, that should be detectable if you have something like 10 milliarc seconds. And maybe even with 20 microarc seconds, you will be able to see some traces of that. So maybe within the next years, we will hear something about the direct detection of the curved space around the black hole in the center of the Milky Way. So that's one way to go. Another way to go is to extend the baselines by using satellites. There are lots of efforts to do that. The Japanese were quite successful to have a small satellite. And finally, after 20 years of fight, the Russian satellite, which was originally called Radioastronomie, which is now Spectre, I don't know how to pronounce that, was started in July. This is just one baseline, but the satellite has a strong elliptical orbit. So if you collect many baselines, you can also reach something between 10 and 40 microarc seconds. But it's a very time-consuming experiment, and the sensitivity is not very high. So there are first results, first detections, but not yet any indication of a shadow of a black hole. So the third way, go back to the roots. So why going back to these primitive telescopes Karl Jansky has built? This is much cheaper. If you want to build big telescopes, you have to spend a lot of money. But if you go to low frequencies, then the telescopes get really cheap. That's why the low-frequency array is built up, or was built up in Europe in the last 10 years, with contributions of many countries here. So mainly in the Netherlands, so 36 stations are in the Netherlands. There are 6 stations in Germany. There's one in France, one in UK, one in Sweden. The 3 Polish stations are now funded, and they are obviously start to build next year. Ukraine is uncertain, Italy is uncertain, and also the other 3 stations in the UK are still uncertain. So with such a big telescope, with relatively low investment of money, you can do something much, much better than Jansky has done, because now we can build a pure software telescope. No moving parts, no mirrors, simultaneous multi-beaming, very low costs, but the technological challenge is very high. How to do that? This is a classical telescope. You have a big mirror, you have to move it, you have to maintain it. It costs a lot of money, and it has to be maintained regularly, whereas a software telescope just has many dipoles on the ground, and the orientation on sky is done by phase delays, by electronic phase delays. So you introduce phase delays between the individual dipoles, and then you look in different directions. These phase delays can be done simultaneously in different ways, so this telescope can look in different directions simultaneously. It's just a question of computer capacity. So this is a very clever design, which is now possible because we have the computers, and this is how it looks like. Not really attractive. You see, this is the LOFAR telescope at low band. It's just wires. So you don't see the telescope. This is a plastic piece here, and then there are 4 wires to the 4 directions. This is just a ground plate to avoid the stray radiation. This is in the nanometer range, and then at the shorter wavelength in the high band, there's some metal pieces hidden in the styrofoam boxes here. Then this is covered by plastic here. Doesn't really look attractive, but these things are really cheap, so you can build thousands of them at very low costs. This design has been done by Astron in the Netherlands, and it is really successful. So this is the core station in the Netherlands. So they built an artificial island. So these things are the high band tiles here, which are covered by plastic. And the low band you cannot see. These are these fields here, which are in between. And then in the Netherlands, everything is below the sea level. They have to have a ditch here, and that can be used also for skiting in the winter. So Dutch people like to do that. And in Effelsberg telescope, we have a low band and a high band field also was established, and you can see these things here just next to the 100-meter telescope. So both of these things are almost 100 meters, so we're a 300-meter telescope. So this is the classical one, and this is the high-tech one. It doesn't look like, but in fact it is. So as I said, so one dipole can see the whole sky. So if you have one station, you have to combine all the dipoles, and then you have a certain beam in one direction. At the same time, you can have a second beam. We can have up to 250 beams on sky at the same time. We can look at 250 different directions at the same time. We cannot trace the whole sky, not yet. This is just a bandwidth problem. And if you do the same with many stations, then we can synthesize, like with the interferometer, the whole beam of one station with very high resolution. So you can have 250 directions on sky, and in all these directions you can have a high-resolution picture. I will show examples of that. So this is how a simple station like Effelsberg looks at the whole sky. So the previous image of the whole sky, that took about 10 years of work with different telescopes. This image has been done in 1.3 seconds integration time. The processing time is still a few hours, so we cannot do a simultaneous tracking of the whole sky at all times because our computers are too slow. But you see basically the same things. You see the Milky Way, you see the main sources, Sagittarius A, Cygnus A, Cas A, I've mentioned that. So you can do in principle a simultaneous monitoring of the whole sky. And this is indeed what people want to do. They want to look for transient signals. The suspicion is that, like with gamma ray bursts, also in the radio range, they are bursts on sky, which last maybe only milliseconds. And they always escape our attention because you very rarely observe a certain region on sky. If you have a LOFAR now in a final, much better computerized condition, then we may be able to see these flashes in the radio. Maybe they are connected with gamma ray burst, maybe not. We just don't know yet. And so very well-known objects can be studied with LOFAR already. This is a Crab Nebula, looks very similar to the optical range here. This is again a magnetic filamentary structure here. So this is a supernova of 1045, and this shows the power of the LOFAR telescope. So this is an observation of a few hours with a few stations with relatively small bandwidth. So this is a field on sky over 12 degrees here. So all these sources are radio sources here. There's some distortions here. And interesting thing is that in the middle here, this is the galaxy M51, which is seen here. So we can see radio emission around galaxies. I come back to that in my last lecture, but we see already a lot of sources. At the moment, we are compiling a catalog of the whole sky at that frequency range here between 120 and 180 megahertz, which will show probably several million radio sources, and that will be used as a catalog for future radio studies. So this is ongoing work with the LOFAR telescope. Also, radio galaxies are nicely seen. So this is again Virgo A. I've shown that already. So this Virgo A is the center of the Virgo cluster. So all the Virgo galaxies are somewhere scattered around here. So it's between 12 and 13 degrees declination here. But what we see is a big radio halo around M82. And this is the connected with the outflow of Virgo out of the active galactic nucleus, and that filled an enormous volume around Virgo A with magnetic field and cosmic rays. The main aim of LOFAR was not to observe galaxies. The main aim was to look for this one. This was the main motivation to build LOFAR, the epoch of reionization. I mentioned structure formation already. So there is the idea that this was a CMB where has been studied or is being studied with Planck, that later, after about 1 billion years after the Big Bang, structure should be formed out of the gas. So this is the CMB. So this is the ionized part. The CMB is the universe becomes neutral again, and in the epoch of reionization, the first galaxies, the first AGNs, the first stars, they ionize the universe again, and they form structures. And this is the idea. These are simulations. So what should happen? So you have a fully neutral universe beyond redshift of 12, and then the first stars, the first AGNs, they start to be formed, and they put energy into the interstellar medium. This energy produces Strömgren spheres, so regions of ionized gas, and this ionized gas then combines to be re-ionized. And according to the predictions, this should happen around redshift of 10, and redshift of 10 means at frequencies of 140 megahertz, redshifted H1. So the H1 line is normally at 1412 megahertz. You have to divide by Z plus 1, so you arrive at around 140 megahertz. So LOFAR was mainly built to detect what is predicted here. If the universe has slightly different development, and that happened already around 100 megahertz, then LOFAR has a problem, because 100 megahertz is in the FM band. And the FM band in Europe is completely covered. You have no chance. And then the Australians have to take over, and then they will be happy because they are building competing instruments also to detect the epoch of reionization, the millimeter wavelength array, MWA. Also the Americans, the long wavelength array, the LWA, it's also looking for similar signals. So let's see who will be first. So LOFAR is already collecting data, and they promised within a year they will have results on that. Let's see whether they are successful. If not, it may be that the prediction is wrong. Maybe the epoch of reionization happens in the FM band. If God is really very nasty to us, it put it into the FM band. Or the signals are just much weaker. Or, I'll come back to that later in my last talk, the predictions are wrong because they neglect magnetic fields. Because if there are magnetic fields, then all that could be completely wrong. So this is one of the main drivers, but LOFAR can do other big things. Okay, and LOFAR is a pathfinder to the dream of all radio astronomers, the square kilometer array, and this is really what we all would like to have in future. The square kilometer array is a worldwide effort to build the biggest and most powerful telescope ever built. And as indicated, it should have a collecting area of a full square kilometer. Whether we ever achieve that, this is a different question, but we still keep to that name, SKA. So there are different concepts. So there's basically the upgraded LOFAR or MWA. These are dipole antennas, look a bit more fancy than just simple wires here for the low frequency range between 50 and 300 megahertz. Then the mid-frequency range is something like the LOFAR high band, but not with black plastic, but with white plastic, because black plastic is really bad in the Australian desert. It would heat up enormously, so you have to cover it with white. And then you have to have simple mirrors for the high-frequency band from 350 up to 40 gigahertz or whatever. And as you can see in the horizon, you need thousands of them really to have a full square kilometer. So these are the concepts which are under investigation. So the question is where to build this telescope, and it's quite clear that Europe is not the best place. ROFA was built in Europe for practical reasons, but we have to fight with RFI because it's at 130 megahertz. It's full of RFI. We can do it, but of course there are much better places on Earth. So the best places are South Africa and Western Australia, and that's where the telescope will go. So this is how it looks in Europe. So the SKA band is completely covered by RFI. You can find gaps here, but to fight with RFI is really difficult. If you're at a small city, maybe Canary Islands, you're slightly better. But SKA site, Western Australia, is really perfect. So you have some weak interference, but not much. The FM band, by the way, is this one here. So there's no FM in Western Australia. You can test yourself. There will be no emitter in the FM band possible. So where will the SKA be built? So in Australia, so the low and high frequencies will be built there. Whether there will be extensions to the Eastern Australia or Tasmania is not clear. Probably it will concentrate to Western Australia. And the second site is the South African side. It will have the medium and the high frequencies. So why splitting that into two different locations? Nobody understands it. At least no scientist understands that. This is a political decision. They couldn't decide between the two competing countries, so they gave both part of it. Okay, a compromise. Because South Africa wants to invest money, but only if they get the telescope. Australia wants to invest money, but only to get that. So to get maximum input from the countries, obviously that was a possibly wise decision. Who knows? You see the problem with Africa. We want to have long baselines, and there are some countries you would better avoid because they are not very stable, and sometimes they are extremely unstable here. So they have nice states. So there's Ghana, very quiet, peaceful state. Namibia is very quiet, peaceful. Okay, Madagascar, mildly. Mozambique, okay, let's believe that it's stable. Then Kenya, but all the countries in between you better avoid. So it's a problem for the South African side with the extensions here. Okay, what is the timeline? So yesterday I changed the timelines again because we are always shifting, because we need a lot of money. Phase 1 is now thought to start in 2018. Early observations 2020. So just calculate in your head whether it still fits to your personal career plans. That means you have to hire people now. So it's a good time now to go into the SKA project because enormous amount of good people will be needed. And the phase 2 construction, 100% area, okay, this is still unclear whether the money will come. So if the phase 1 with 10% area is successful, then maybe phase 2 will be done. So phase 1 is already 300 million euros, but that should be split between 10 or more countries, so it should not be a big problem. So there are 6 key science projects: dark ages, dark energy, as usual, galaxy evolution, very interesting and important, testing theories of gravitation with help of pulsars. Magnetism has made it to one of the key science projects, Cradle of Life. This is just looking for planetary systems, and then exploration of the unknown, something we don't know about yet. And as I said before, so if LOFAR doesn't succeed to see the epoch of reionization, and also the MWA and LWA, the other smaller instruments don't, then maybe the SKA will be able to see that. But the SKA will run for the dark energy experiment to measure redshifts of hundreds of millions of galaxies. I don't know who will reduce all this data, but this is at least the plan for the SKA to look for the dark energy. And so people expect that to detect around 30,000 pulsars in the Milky Way. So these are the pulsars known, and the blue ones are the ones to be detected. This is extremely interesting to improve the knowledge about pulsars, but also about the Milky Way. I will come back to that in my 5th lecture. And then with pulsars, using pulsars as clocks, we should see gravitational waves passing by, because when the local clocks will show deviations, and they will show deviations in a systematic way. And so by observing a network of pulsars, we should be able to see gravitational waves directly. So this is another Keysunge project for the SKA. And then we hope to see in the Milky Way at least 1 or 2, maybe 3 of pulsars orbiting around a black hole. And this gives an extreme test of gravitation, of general relativity, because the curvature of space is extreme, and that could allow to test it to much higher accuracy than above. But the prediction is in the Milky Way we may have only a few of these. So maybe we are lucky out of the 30,000 to find a few ones, maybe not. And magnetism. So this is what the outreach committee thought how a cosmic magnet would look like. Do not completely agree with that, but at least it is nice for the public. Cradle of life to see protoplanetary disks and look for biomolecules, but that needs high frequencies. So on the first phase of the SKA that will not be done. That is done for later. And as a byproduct, also SETI will use the SKA. And so if there are airport radars out to 30 light years, probably not. But ionospheric civilizations using ionospheric radars, we may be able to see them. If they have Arecibo-type planet radars to trace their neighbor planets, we may be able to detect that out to 15,000 light years, which gives a slight chance of seeing something. Now, radioastronomy really believes that SETI will be successful, but it doesn't cost much. It's just a byproduct of what we are doing, so why not? So, we need money, and we need excellent people, and hopefully among you there will be people joining the SKA project. So it's really exciting, and just strongly recommend to think about that, to join the SKA project. Thank you. So should we continue or have a break now? So what is the idea? Okay, coffee is at 11. Okay, we continue at half an hour, and then let's see now. Okay, so questions? Sorry that I did not mention all the Australian project in full detail, but the project will last for a long time, so there will be a phase 2, then maybe there will be a phase 3. So if the product is successful, then I don't doubt that. Like with ESO, you see, we need a new organization which is in continuing. So ESO has never problems to find the next project, so they have a continuous run. So that's why so with LOFAR we have a limited time. So LOFAR even has to be removed. So that's a law. No? So it can work for 5 years, maybe with some extension, but then everything has to be removed completely. But the SKA is too big, so you cannot easily stop such a project. No? You will always have ideas to upgrade the telescopes and to maybe to add new receivers, and so if it once runs, the momentum is so big that I think you cannot stop it's like a big train. Yes. Sorry? The weather. It's at high frequencies. So at high frequencies we have lots of distortions. So then the various molecules in the atmosphere, they start to absorb a radio emission. They also emit. They also have emission lines here. So that's why starting at so in Effelsberg, at all long wavelengths down to about 10 centimeters, we are more or less weather independent. But then it slightly starts to affect. So at 6 centimeter, we need a relatively good weather. At 3 centimeter, even better, and then 1 centimeter and lower, the atmospheric conditions strongly affect your observations. And that's the same for the SKA, but it's less severe for interferometers, because interferometer combines signals from many telescopes, and if the weather is different, because this is a correlation technique, then the weather would drop out. So it's like when we observe with 2 horns on sky with Effelsberg. So the weather is the same for the 2 horns at the same time, but if you observe the source, if you scan across the sky, then the source will be observed at different times, and then the weather can be cancelled. But weather is not the real problem, so I think South Africa and Western Australia, they normally have good weather. And with LOFAR also, the weather should not be a problem, but in fact it turned out to be a problem, because if you have snow lying on this plastic coverage, then you cannot observe anymore. If you have storms, then the simple light dipoles are just blown away. So we have lots of weather problems which you did not expect. So we have ice on the wires when we cannot really observe. So this is a different sort of weather effect. With the SKA, there's some worry that maybe the heat in the desert will cause problems. So the electronics, they need really good cooling. So they need a lot of energy just for cooling to keep everything running. And that means you need enormous energy supply. So you need to build solar energy power stations. And you need that not only in daytime, you need it at nighttime. And at the moment, there are no batteries who could just continue SKA operation during nighttime. So these have still to be developed. Sorry? There's nothing there. So yes. Now, I think you don't want to transport energy, you want to produce it on site. And the solar energy is a way to go in the desert. So people have the ideas that it should be all green energy, so you should not use energy from somewhere, transport it from anywhere. And I think there are megawatts of energy are really needed. I don't know whether the Australians would like to put megawatt lines to the western areas. And I'm sure the Aborigines would not like that idea. Yes. The first? Yeah, there will be early phases. I did not mention at all. Should mention that now. There are 2 more pathfinders running already. So there's the ASCAP, the Australian ASCA Pathfinder, and the other one is Meerkat in South Africa. And so these 2 telescopes are already partly running. So that means the SKA has started already by these 2 projects. But these projects are time limited, so they have funding for a limited period, and both the telescopes have problems with their funding. So the smooth transition to SKA still has to be achieved, but it's hopefully will be working. So that means SKA observations have already started. So ASCAP has started, Meerkat has started. So it is. I think this is already a way to start now. But the full SKA phase 1 that will take some more time. But of course you have to build up the telescopes slowly, so that will take several years until they are all on ground and tested. Yeah. Mm-hmm. Yeah. Mm-hmm. Mm-hmm. Yeah. Well, that's all done. That's all done digitally. So we have clocks. We have clocks which are setting the. Which are setting these are digital clocks which set the frequency range. So you always observe over a certain frequency range. Yes. No. Yeah, we take a continuous signal. So we have a range where we can detect the signal, and then we just with software by an autocorrelation we just split the signals into channels. So that's done like in classical spectroscopy. And so there are different clock settings, so you can observe in different frequency ranges, and you can switch between them. But for instance, between 120 and 180 megahertz, we can observe simultaneously. If you want to go to higher frequencies, then we have to change the clock setting. Then we can move the whole band to a higher frequency. Mm-hmm. Mm-hmm. Well, that's simultaneously. So we get the full emission, and then we split that into frequency, and then we trace this over time. And the low band, if you go between 10 and 80 megahertz, then we have to use a completely set up the different antennas, because where the high band antennas will not be sensitive. It's just a question of size. So the metal dipoles, which are in the styrofoam, they are about that size. So they're detecting meter waves, whereas the wires, they are about 2 meters long. So they are up to 10 meters. So just a question of size. So they will not be sensitive to the. So a certain dipole has a sensitivity over a certain frequency range, but there are limitations. So there's just a band pass. So you have maximum sensitivity, then it drops down on both sides. Yes. So this is why we have 4 wires. So we see we have the both polarizations, and also the styrofoam we have cross dipoles. So they're always cross dipoles. It's not like in Effelsberg where we see right and left-hand polarization and we correlate them, but we see really X and Y. We detect linear polarization directly. So this polarization is the difference between X and Y, and the other Stokes parameter is slightly more complicated. But basically we can see polarization, yeah. So this is a basic property of all radio telescopes, that polarization is something which is automatically provided. Not like in optical, where you have to have extra polarizers or analyzers to split your light into polarized components. In radio, we see the polarization directly, without any extra effort. So we get them for free. Yes. That's much more difficult. It's just because first circular polarization is much weaker. In principle, we could do that, but in fact, with LOFAR, nobody has ever tried that. There's only very few objects who produce circular polarizations, sunspots or Jupiter bursts, and so they are going to do that. But it's much harder to do because the levels are really low. Oh, sorry. Now for Jupiter bursts, it's not true. So Jupiter bursts, they can very high circular polarization. Yeah. So okay. So that's a possibility. Mm-hmm. With Effelsberg, if we have circular polarization, then detection, we have right and left hand, we could just simply subtract the two. But that is also difficult because the weather will be different for right and left hand, so you're also sensitive to weather effects. So that's why circular polarization is not easy to do with a single dish telescope. With a VLA, it's easier. So that's much more straightforward. Okay, then next round. Okay. So, we can. No problem. I think we can start, and then I think we all need coffee, and so without coffee, this is okay. So number 3. So how to measure magnetic fields? Come on. 45, slow. What's going on? Okay. So, lecture number 3, how to measure magnetic fields. So, as I said in the beginning, it's not easy to measure magnetic fields, and but we have several different methods to measure them. And I will just briefly introduce them. So the easiest way is to use magnets, so magnetite stones here. But unfortunately, we cannot move the stones to the cosmic objects. So these stones are known since long, and at least 2,000 years. And so magnetism comes from Magnesia, where the stone was found in Greece. And I know if there are people from Turkey here, that Turkish people don't like that because we have a similar village in Turkey called Manisa, and so the competition is as usual between Greece and Turkey, who was first. Okay, so I decided Magnesia sounds a bit more reasonable, so that's where the magnetism comes from. the compass, the use of magnetic stones, was already found in China about 200 years before, and sailors are known to have used them already in the year 1000. So these are two examples of very early compasses. So this is a spoon, this is a fish used by Chinese sailors. So as you may know, Chinese sailors were extremely successful on the oceans, but then for some reason they stopped sailing. Obviously the emperor didn't like this anymore, and that's why it's not so much known, and they were not such a sea power as Spain or Portugal or Great Britain was in the later times. So magnetism can be simply described by the Maxwell equations, as you all know. And so that again shows the asymmetry between the electric charges and the magnetic charges. So magnetic charges do not exist, so no monopoles. Divergence B is equal 0. And that means magnetic field lines are always closed in itself. So this is a property. So when I was young, there was a discovery of a magnetic monopole on a Valentine Day of 1982 by Cabrera. But that could never be repeated, and an experiment which can never be repeated is officially non-existing. So this detection of a monopole had to be officially withdrawn, although Cabrera never found any other explanation for his detection, that suddenly the current in a superconducting spoil was suddenly changing by exactly the amount expected from a monopole. But that was on a Sunday, and nobody was in the lab at that time. So okay, so we have to put this to 0. We have no idea why the non-monopoles are non-existing. There are some ideas about cosmology, inflation, cosmology, why monopoles are so thinned out by inflationary expansion of the universe, but I'm not sure whether this is a good explanation. Okay, so how can we measure them? So we can trace particles. So this is what synchrotron emission does. So particles can travel around magnetic field lines on circular orbits due to the Lorentz force. If they are at some angle towards the magnetic field, they make spirals. And if the magnetic field is inhomogeneous, you can have a magnetic bottle. You can store particles within a magnetic field. So this is things which can be easily applied to cosmic observations. So these are the different methods, and I will briefly discuss all of them. So some of them before coffee break and some of them after. So polarization by dust grains, and the Zeeman effect, Goldreich-Kilafis effect related to Zeeman, and then rest is synchrotron, total synchrotron, polarized synchrotron, Faraday rotation, and Faraday depolarization. Faraday rotation has been partly covered by Klaus yesterday, so sorry, Klaus, if I repeat things again. But to be complete, I thought I will discuss all these effects. So the first and the best known detection of magnetic fields in the universe is by aligned dust grains. So let's suppose that there are elongated dust grains, and we believe that all dust grains are elongated because spherical dust grains don't exist. If they are elongated perpendicular through the magnetic field for some mysterious reason or mechanism, then you get more absorption along the major axis and less absorption of the starlight, the background, along the minor axis. And that means you have polarization which is parallel to the magnetic field line. But if the dust grain is not absorbing but emitting itself in infrared because it's a warm dust grain, then the things reverse by 90 degrees, because then you get more emission along the major axis and less emission along the minor axis. So then enough, you don't need any star in the background anymore. In that case, the polarization is perpendicular to the magnetic field line. So that's very easy to keep in mind. The problem is how to get this dust aligned. And the original idea of Davis and Greenstein in 1951 was so-called paramagnetic dissipation of energy. So don't read their paper. You cannot understand that. I don't understand it, and nobody believes this anymore because this mechanism will not work. Sorry, the dust is spinning, yeah. I forgot to mention that. Yeah. It has to spin around the omega. It has to spin around this is the magnetic axis, yeah. No, It depends. If you look from top, if you look from here, it's spherical. It only works if you look perpendicular to the magnetic field. Only look from here, right? Okay, so that's why Huang and Lazarian had a more clever idea. I also don't understand the details of that. It's radiative torque alignment, so it works with the radiation torques exerted on the dust grains, and this is much faster. So if you really want to understand that, you have to dig through that paper. It's a long, long paper, and I did not understand it fully. But that seems to work, and this is generally accepted as being the clever, the more modern interpretation of the alignment. Okay, but nature shows that it really works. So if you detect many stars, 5,500 stars, and you trace them and you plot their polarization planes, and remember optical is parallel to the magnetic field, then you find a very nice alignment along the galactic plane for the distant stars. For the nearby stars, there is some chaotic distribution here. So that means locally the magnetic field is relatively chaotic, but on large scales and on long distances, the magnetic field is oriented along the galactic plane. That is known already since long. That has been done already many times before. So that is known since the 50s that the magnetic field in the Milky Way is along the plane. That comes from the optical polarization. This is a more recent one, and I know that colleagues in Brazil, they are working on a much more extended star catalog, but I did not see yet results. So does anybody know about that? No, our Brazilian colleagues not here at the moment. Okay, so then some clever people in the UK thought, maybe we can apply it also to diffuse emission. So let's measure polarization of a galaxy in the optical light, like M51. And the diffuse emission of a galaxy in optical is just a summary, is just an integration of a lot of stars. So that should also work. And Scarrett claimed that this is a detection of the magnetic fields in M51. And indeed, partly it is along the spiral arms and is consistent with what we see in the radio. But there is a big uncertainty. Because if you treat diffuse light, then part of the diffuse light is due to scattering of the starlight at dust grains. And scattering produces polarization, very high polarization, up to 100% under certain angles. So we cannot separate the alignment, the Davis-Greenstein effect, from scattered light, unless we have different colors, and we can do a color separation of the emission. But these degrees of polarization are extremely weak. They are of the order of 1% or less. And this is broadband. If you want to split this into filters, it's completely hopeless. I can tell you I tried myself. That was one of my unsuccessful research projects. I did a lot of observations on a ESO telescope in Chile to do this much better, and then we gave up because and nobody tried since then again. So to do diffuse polarization in optical is very hard. Okay, maybe one of you has a better idea or a better instrument in future. It would be interesting to try again, but it's really hard. So, yeah. Yes. Yes. Yeah, you need to model that. You need a source distribution. You need a model of the dust grains distribution, and then you have to see how much scattered light. Yeah, but still there will be some leftover polarization, because polarization can be very high by scattering. If you have you need a systematic offset between the sources and the scattering sources, the light sources and the scattering sources. Then you should get polarization. If everything is mixed, okay, then you're right. Then the polarization should be zero. Yes, but you see, the sources and the dust is always offset. The dust is at the inner edge, and the main sources, the stars, are in the spiral arm. So you have a systematic offset. So nobody tried that. So that would be nice. Would be interesting to test that, whether you really can get scattered light. So we decided we would not do this. It would need a proper model. But our suspicion is that even if you have to explain a percentage of less than 1%, it's relatively easy to get that. Okay, anyway. So contamination by scattered light is a problem. Degrees of polarization are very small, so you need very bright sources to have high signal-to-noise, and the physics of grain alignment is not understood. So that's not very encouraging. But everything which are not very encouraging are something which can be done by somebody in future better, maybe one of you. Okay, so what is much easier to go to submillimeter? Submillimeter, you don't have polarization by scattering or by absorption, but you have polarization by emission. So you don't need a background source. You see the dust grains emitting themselves. And that is much easier if you have the good instrument. SMA is on Hawaii, so with very high resolution and 870 micrometers, so submillimeter here. This is a polarization pattern of a molecular cloud. This is a rotating molecular cloud, and it seems that you directly see the infall of the gas, which tracks the magnetic field into the molecular cloud. So amazing. So when I saw this the first time, I thought, oh, okay, this is the proof that magnetic fields may affect molecular clouds. I'll come back to that in my talk on Thursday about the Milky Way magnetic field. It has to do with ambipolar diffusion. So it looks very promising. The problem is that these sources have to be really bright. You have to have really high resolution to detect them, because only cores, rotating cores of molecular clouds can do that. So again, degrees of polarization are low, molecular clouds are small, and again, the physics of grain alignment is not understood. That's also true here. Can hardly be measured. There is a method, the Chandrasekhar-Fermi method, developed in '53, very clever. And Chandrasekhar and Fermi, both very famous scientists who did a lot of different research, also worked on magnetic fields. Nobody knows that. Competition between the magnetic force and turbulent gas motion. So a strong field, the magnetic field lines should be straight. There's very little dispersion of them. If the field is weak, then the turbulent motion of the gas tangles the magnetic field, and you get a very high dispersion. So by just comparing the forces, you can get an estimate of the magnetic field strength. If you know the gas density, if you know the turbulent velocity, it can be estimated, and the dispersion of the polarization lines. Very clever method. And it works, really. You get micro-Gauss levels in that paper. So this is really, so you should really look at this paper. This is on APJ, it's only 3 pages. So these are papers are really fundamental papers, are easy to read and fundamental ideas. Extremely nice paper. It should be read by everybody, not like a difficult paper, so I have to cite here. Okay, so there's some problems with that. The dispersion of polarization vectors is not only due to magnetic fields, it's also due to instrumental errors. There's a lot of geometry, line of sight integration, so you can do much better. There has been a sequence of papers by the American group Hildebrand and also Martin Hood from Canada who improved that. And they also applied it to our radio maps, and it can be done in the same way. And this is a paper that has been published just this year. So this method is really very clever, but still it is only an estimate. So you can do something, but it's not a precise measurement. It's just a very rough estimate. Okay, so let's go to a more precise method. So Zeeman effect is our best method because you have a direct trace of magnetic fields. So Zeeman splitting produces 3 lines here. So there is the pi line and 2 sigma lines here. So if you look along the magnetic field, you see only the 2 sigma lines here. They are circularly polarized. If you look perpendicular to the magnetic field, then you see the 2 sigma lines and the pi line, and all of them are linearly polarized. So the problem is this, you can relatively easily measure, but here you mix all the 3 lines. This is almost hopeless to be measured. This is why almost all measurements of Zeeman effect rely on the longitudinal effect. So you look along the magnetic field and you see a splitting into left-hand and right-hand circular, and the difference between left and right-hand gives a very nice profile. So if you have a telescope which can measure circular polarization, a colleague asking Circular polarization has just disappeared. So you need a telescope which is very good to measure circular polarization. So don't use Effelsberg. You need to use a telescope like the Australia Telescope Compact Array is ideal for that because it can measure circular polarization nicely. Then you see this typical profile in the difference between left and right-hand circular. So that has been measured since decades, and a lot of measurements have been done. So you see these typical profiles here. This is the total line. This is the nice profile here. And you can really measure fields down to less than a milligauss, which is already a big advantage. In the past it was milligauss. Now you can measure less than a milligauss here. This is in CN, and this CN molecule transition has 7 hyperfine lines, so you can measure these several times and can improve your result here. And you can also compare optical polarization, dust polarization with Zeeman, and you can get a 3-dimensional picture of your magnetic field. So, as I mentioned, the polarization in the dust gives you the perpendicular component, the projection of the field, 140 microgauss, and this gives a line of sight by the Zeeman effect, plus 11 microgauss. So you could now think about that it gives a 3-dimensional picture of the field, but you have to be careful because the dust polarization, and this is OH Zeeman, does not trace the same regions in that molecular cloud. This is the inner densest dust core, and this is OH is in the outer envelope. So the difference may also be due to a decrease of magnetic field strength from the inner to the outer part here. But in principle, this should work. Okay, so I said linear polarization in Zeeman effect is very hard to measure. But there's an exception. If the conditions of the 2 lines, 2 sigma lines, are not symmetric, if you have unequal populations of the different sublevels for whatever reasons, because of temperature differences or whatever, if you have a gradient in optical depth or velocity, or you have an anisotropic velocity field, then there is linear polarization. And this is called the Goldreich-Kilafis effect. And the problem is because the sigma and the pi lines have different orientations with respect to the magnetic field, you'd never know whether your linear polarization is parallel or perpendicular to the magnetic field. So that means if you detect this effect, you don't know the magnetic field direction up to multiples of 90 degrees, which is a bit unfortunate. It has been detected in many objects, and I'll just give you one example, a recent example. It has been detected also in external galaxies. So this is M33. This is a paper of the synchrotron polarization I was involved in myself. And then in these dots here, they measured the CO line and detected linear polarization in the CO lines here, all these dots, and then they measured the difference between the polarization of the CO line and the polarization in synchrotron, and they found 2 peaks at 0 and 90 degrees, exactly as expected for the Goldreich-Kilafis effect, because the CO polarization is ambiguous by 90 degrees. And that means the magnetic fields in molecular clouds are obviously aligned with a large-scale spiral magnetic field, which is very surprising because molecular clouds are rotating and they should be decoupled from the surrounding magnetic field. So why is this? I don't understand that. And I'd be a bit skeptical, but okay, the result seems to be convincing here. So this is, for my understanding, the most interesting application of the Goldreich-Kilafis effect. So what are the problems with Zeeman splitting? The effect is weak. You need low instrumental polarization, and even big telescopes like the GBT, the new big US telescope, 102 meters, has big problems to measure the Zeeman effect because their instrumental polarization level is very high and is very hard to correct for that. The H1 line traces only diffuse warm gas, and the other suitable lines for CO are much weaker, so you need really very bright objects. And the Goldreich-Kilafis effect has this very unpleasant ambiguity by 90 plus minus 90 degrees. Okay, and that's maybe a good point to break. Go to synchrotron, because with synchrotron life is much easier. This is why I recommend synchrotron to do magnetic field measurements. Okay, I think it's time for a break. Yes, of course. Yeah, it's true. Yes, I know. I didn't mention that because it's more for solar physicists, and this is not in our range. So it's very similar, yeah. 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 It's history. Yeah, I can complain about history. That's right, yeah. Probably there are two different communities that didn't talk to each other. Because we don't talk too much, so much with solar physicists. This is another problem. Yeah, yeah, you're right, yeah. Yeah, yeah, yeah. Yeah, so maybe you're right. So I don't know the Handler effect so much because they're very similar. That's what I know. No? I just didn't mention the Handler because this is something which is used by solar people and not by us. Because in the interstellar medium, this does not apply. No? Okay, so time for break.